Hey y'all, welcome to Miss Clark's chemistry class. In this lesson, I'm going to teach you how to name and write formulas for ionic compounds. Now, I do have other lessons on my channel for this specific topic, but they're kind of broken into little micro lessons. I'm going to lump everything ionic compound together in this one lesson because this is how I teach it in class. Go get some notes, get a periodic table, and let's get started. Okay, so we're going to work on naming and writing chemical formulas. Specifically, though, for ionic compounds. Now, there's a specific set of rules for ionic compounds and a different set of rules for covalent compounds. And let's think about that for a second. When we were talking about the electron dot for ionic compounds, we had a dot and we would take that over, we would draw it over, we would realize we need another, we would say that the sodiums are all +1s. The nitrogen is -3, and then we would realize that we needed 1, 2, 3 sodiums for every 1 nitrogen, and we used our charges. And I didn't have to tell you how many sodiums and how many nitrogens. I just had to tell you sodium and nitrogen, and you would do this whole process and figure out that it takes 3 sodiums to match up with 1 nitrogen. But then we also talked about covalent bonds, and I did have to tell you. I would have had to tell you that 1 nitrogen is bonded to 3 H's, and then you would have used your information and you would have drawn this structure. Very different processes. So when we name them, very different naming rules. And again, today, I'm talking about ionic compounds. This situation here, we will come back to this at a later time. Okay, so we're going to talk about naming and writing. So if I were to give you a formula, you would have to tell me the name. Or vice versa. If I give you a name, you have to tell me the formula. I am going to start with talking about how to write the formula. But before we go any farther, I want to talk about this thing called a polyatomic ion. We can let the word kind of tell us what it means. We know that poly means many, several, more than one, couple, few. Atomic, atoms. So we're going to have several atoms working together as a unit, but it has a charge, so it's going to be an ion. Okay, let's write that definition down. A polyatomic ion is several elements, it's actually nonmetals, several nonmetals, so they are covalently bonded, working as a unit, but they have a charge. And since they have a charge, we've got to call them an ion. And since they have a charge and they are an ion, they are going to be a part of ionic compounds. Let me show you a list that I have. Now, this is not the list that I give out in class. I actually didn't have that with me, but let me show you a really common list as well. Okay, here's my list. So we see how these are several elements, all nonmetals. They're bonded together covalently, but they have a charge. The list that I pass out in class has all of these on there, plus a little bit more. I want to call your attention to ammonium. Ammonium is a polyatomic ion that's positive, but all the rest of these are negative. And if it just has a negative sign and no number, that's a -1. A positive with no number, that's a +1. Again, these are covalently bound nonmetals working as a unit, but they have a charge. We're going to be using these. I'm going to come back to these a few times. Okay, so back to writing the formula. When we're writing the formula for an ionic compound, the number one rule to remember is that the net charge has to be 0. Has to be 0. That's the number one rule. I'm just going to go ahead and write a name, and we're going to write the formula, and I'm just going to show you how to do it as we go. So if we had sodium oxide, the very first thing we need to do is write the symbols and the oxidation numbers for the metal and the nonmetal. So sodium is the metal. Sodium is an Na. You need your periodic table out. What group is it in? What's its oxidation number? Sodium is a +1. Oxygen is a -2. We need this to equal 0. So how many sodiums are we going to need to equal an oxygen? So if we think about this, if sodium is a +1, but oxygen is a -2, well, it would take 2 +1s to equal a -2. +1 + 1 is a +2, and we already have a -2. So it took 2 sodiums. So we're going to have Na2O. Sodium oxide, Na2O. Since sodium was a +1, we needed 2 +1s to equal out and get a net charge of 0 with this oxygen's -2. Let's look at another example. Let's look at aluminum chloride. Aluminum chloride, we need to write the symbol, aluminum. Oxidation number, aluminum is in group 3, so it's got a +3. Chloride. Now, I didn't mention this a second ago with oxide, but let's back up for a second. We have this IDE ending. When you have an IDE ending on the second name, that means this element came from the periodic table. So chloride is just regular old plain chlorine, and chlorine has an oxidation number of 1. So if we're looking at this, we're just going to logic through it. The positive side is worth a +3, and the negative side is worth a -1. How many negatives will it take to equal the positive? This one is as straightforward as the one we worked before. It is going to take 3 chlorines. So our formula is AlCl3. Let's look to see when the oxidation numbers are the same. I'm going to do aluminum again, but this time I'm going to do nitride. Again, think about that ending IDE. That means that came from the periodic table. Nitride, that is just nitrogen. Nitrogen has a -3 oxidation number, and we just said that aluminum had a +3 oxidation number. Now, +3 minus 3, that already equals 0. So it's just going to take 1 aluminum and 1 nitrogen, AlN, aluminum nitride. Let's look at another example. What if I gave you calcium phosphate? I hope you are noticing this ending is ATE. Now, if the ending is anything other than IDE, it is a polyatomic ion. Did you hear that? Let me say it again. If your ending is something other than IDE, it's a polyatomic ion. Let's pull that list back up real quick. Okay, so I've got my list up. Let's look at calcium. Calcium is Ca +2 because it's in group 2. Phosphate, though. Look, phosphate's right here, and phosphate is PO4 and a -3. So we've got a +2 and a -3. If you remember us doing the Lewis dot structures, I had said, this is the hardest one we're ever going to do. And it was hard because it was a 2 and a 3. Now, I don't want us to have to go back and forth and back and forth and back again to figure this out like we did the Lewis dot structure. So I just want us again to use a little bit of logic. I want you to think about the lowest common factor between 2 and 3. Because we cannot multiply anything by 2 and get 3. So the lowest common factor of 2 and 3 is what? Are you saying 6? So we need for the calcium side to be a +6, and we need the phosphate side to be a -6. So how many +2s is it going to take to get a +6? I hope you're saying 3. 3 times 2 is 6. So we need 3 calciums. Now let's do the same thing for phosphate. How many -3s make a -6? Well, I hope you're saying 2. 2 times 3 is 6. We've already got 3. We need 2 of them. So we will end up with PO4. Now that's a polyatomic ion, but I just wrote its symbol. But we're going to have 2 of them. And anytime you have more than one polyatomic ion, they have to be in parentheses. Because we don't want that 4 and 2 to combine. We need to show that there are 2 phosphates. So calcium phosphate is Ca3PO4 2. It looks pretty complex, but we did the exact same thing as we did on all the other problems. We need to do a couple more examples. Okay, let's look at this example, copper 1 oxide. Now, we have not seen an example with this Roman numeral yet, and I'm going to come back to that really quickly. We're going to do this the exact same way. Every single time we've looked at the name, we've looked at the symbol, got the oxidation number, and made them equal 0. We're going to do the exact same thing. Copper's symbol is Cu. Now, if we go look at the periodic table and see what the oxidation number is, go ahead, go take a look. Copper. See it over there? It's in D block. We do not have oxidation numbers labeled in D block. But that's okay, because look, this Roman numeral is here to tell us the oxidation number on copper. Copper, in this instance, is a +1. Now, sometimes copper is a +2, and sometimes copper is a +3. But right now, today, copper is being a +1. And the only way we would have known that as if it told us right here in the name. So we're still on the right track for doing the exact same thing we've been doing. Oxide, that's oxygen, because remember, IDE ending is just regular plain oxygen. So oxygen, -2 oxidation. Copper's a +1, oxygen's a -2. So it's going to take 2 coppers, Cu2O. So we have looked at 3 different examples. We've looked at one where we just had name, and it ended with IDE. Everything on the periodic table. We looked at 1 or 2, just one, that had a polyatomic ion in it. But we still just wrote its symbol, got the oxidation number, made it equal 0. And then lastly, we looked at an example where there's a Roman numeral. But we learned that the Roman numeral is just the oxidation number for the transition metal, because the periodic table won't tell us. But you still just write the symbol, get the charge, make it equal 0. Okay, we're going to switch gears a little bit. Now we're going to talk about how to get the name. So we're going to be naming ionic compounds. We do need to talk about a couple rules before we start talking about naming. Now, this is a binary nomenclature, meaning the system of naming, nomenclature, has 2 names. So if you start writing your name and you've got like 3, 4, 5 names, hello, you are wrong. It only has 2 names. That's going to be your first clue. Now the first name, this is going to be the name of the metal. And the second name, this is going to be the name of the nonmetal. Or really more specifically, the first name is going to be of the cation, and the second name is going to be of the anion. We've already kind of talked about some of the things, and when they come up, I'll remind you of them. But did you notice some of those names had Roman numerals and some did not have Roman numerals? So we need to talk about when to put a Roman numeral, because if we're the one writing the name, we've got to be the one coming up with the Roman numeral. And it's all about this metal. Ionic compounds can be made of one of 2 metals, a main metal or a transition metal. I consider all of the metals in group 1 and 2, and then just aluminum, to be main metals. Metals where you can look at the periodic table and tell what their oxidation number is. Main metals. Transition metals are going to be every other metal. Every other metal is going to be a transition metal. Those are going to need a Roman numeral. If you have a main metal, I like to say we're just going to write it. I'll tell you what that means in a sec. If you have a transition metal, we need a Roman numeral. And if you have a polyatomic ion, again, we're just going to write it. Let me show you what I mean by that. Okay, I have 3 examples here for us. Ionic compound formulas. Look at the metal first, because we have to identify it as main metal or transition metal. Li, lithium. Lithium is an alkali metal. That means it's in group 1. That is a main metal. So we're just going to write it. So I'm going to write lithium. And then what? That's multiple capital letters put together, working as a unit. That is a polyatomic ion. So if we scan back through that polyatomic ion chart, let me pull it up again for us. CO3, right here, carbonate. And so again, we're just going to write it, carbonate. So when it's a polyatomic ion, we're just going to write it exactly how it is. Because remember, that ending tells us a story. When it's IDE, that means that element came from the periodic table. When it is not IDE, it's a polyatomic ion. Not IDE, it was a polyatomic ion. Let's look at this next example. Sr3N2. Sr, we got to look at that metal first. Strontium, it's in group 2. Alkali earth metals, it's a main metal. So I'm just going to write it, strontium. Nitrogen, that's our non-metal, but it's from the periodic table. So we got to change the ending to IDE. So we're going to put nitride, strontium nitride. I had another one written up here. I must have deleted it when I took away the polyatomic ion chart. I had NH4Cl. Now, if you remember, I said to point out NH4 on that polyatomic ion chart. NH4 is a polyatomic ion, and it's the only positive one that I'm going to give you. There is more, but I'm only going to give you NH4, and it is ammonium. So when you have a polyatomic ion, you're just going to write it. So I'm going to write ammonium chloride. Because chlorine is on the periodic table, chlorine, we got to change the ending to IDE because it was on the periodic table. We need to look at a few more examples because we have not looked at all the types of examples yet. Now here are 2 more examples, and they look very similar. They have the first metal is the same and the non-metal is the same. Let's look at the metal first. Cu, copper. Copper, that's in D block. That's a transition metal. We need a Roman numeral. But I'm going to go ahead and write copper. I'm going to leave a space for my Roman numeral, and then I'm going to go ahead and finish my name. Oxygen is oxide. Before, when we were writing the formulas for transition metals, not a problem, because the Roman numeral told us the charge. But hello, now we're the one writing the name. We got to be the one to come up with the Roman numeral. And that's okay, because we do have enough information. We know that an ionic compound has to equal 0, and oxygen is a -2. So if oxygen is a -2, what does copper have to be to equal it out? That's right. It's got to be a +2. So we're going to do Roman numeral 2. Copper 2 oxide. Let's look at this next one. Both of these are real compounds. Cu copper, Roman numeral, oxide. Oxygen has a -2. If one oxygen makes a -2, that means the positive side also has to be a +2. But there are 2 coppers. So after we look at both coppers, the total can be a +2. So we've got +1, +1. This is copper Roman numeral 1 oxide. 2 different compounds because we had copper in 2 different oxidative states. I want to just look at a few more examples with transition metals because I don't feel like we've talked about them enough. What if we had something like Ti2O3? Okay, so Ti, that's titanium, and it is a transition metal, so we need a Roman numeral. Dang, I did oxygen again. Oxide. We know that oxygen is a -2. If we logic through this, we have 3 -2s. That's a -6. So that means our titanium side has to be a +6. So what could this charge be where 2 of them equals a 6? I hope we're thinking of 3. Now I have a shortcut. If you multiply these 2 numbers and divide by this number, it will always give you the Roman numeral. Now I ignore the negative because this oxidation number this Roman numeral is an oxidation number, and it is for the metal. It is always positive. So I ignore the sign. So I'm going to take 2 times 3, which is 6, divided by 2, which is 3. It will always get you the right answer. If you multiply the oxidation by how many you have and divide it by how many you have of the metal, will always give you the oxidation number. Let's look at that one more time. Okay, let's look at SnO2. I know, oxygen again. Sn is 10. Roman numeral, because it's a transition metal, oxide. Oxygen is a -2. So we've got 2 times 2 is 4, divided by nothing, which is a 1. 2 times 2 is 4, divided by 1, so we're still doing 4. 4 is IV. We talked about how to write the formula for all kinds of ionic compounds. Ionic compounds that had main metals, that had transition metals, that had polyatomic ions, and the rule was exactly the same. You get the symbols, get the charges, make it equal 0. Then we talked about how to write the names. That if it was a main metal, we're just going to write the name of the metal, the name of the nonmetal, and then be done. If it had a polyatomic ion in there, we're still just going to write it as it is, as a polyatomic ion, and be done. But if our first metal is a transition metal, we must come up with that oxidation number using just the tiniest bit of logic. I really, really hope this gives you a place to start from. This by no means should have you being a pro. This is getting you started. You must practice. You must practice. You must practice. All right, y'all. Until next time. Bye, y'all.